It's question show time. Your questions, my answers, as always, wherever you are across my channel. Question pops in your brain, just write it down. I'll gather them up and I'll answer them here. Just one is best though. Fraser, if we find microscopic life on another world but it doesn't use DNA, how will we recognize it as life? That is a great question, and obviously astronomers have spent a lot of time trying to figure out this question, right? All life on Earth is all related, it all has DNA, but if life formed in some other location, maybe it's not even made of the same kinds of chemical elements. Maybe it's made out of silicon, or maybe it's made of ammonia or methane or all kinds of interesting other chemicals that are possible here in the universe. How do we know that it's even life? And the reality is that there's not going to be any strict definition, but the one that will get you the closest is if it can move. If it can move with some kind of intent. So a good example would be like, say, a tree, right? You plant a tree or a plant, and a plant will move itself trying to orient itself to be able to reach sunlight. And so you can see that the thing is moving. The intent is that it's attempting to maximize the amount of sunlight, and we classify a plant as life. Now, we're actually related to it, we share DNA, but those are the kinds of things. But in general, astronomers, exobiologists are going to have a whole bunch of different methods that they use to try to determine if something is life or not. And they're going to have this huge list, but they're not going to, I mean, obviously you saw some kind of alien monster running around and we find that it doesn't have any DNA, that it would be obvious. But it's going to be things that are microscopic. They're kind of like DNA. I mean, we still argue about whether or not viruses are life here on Earth. And yet, obviously, we experience the impact of viruses. So it's going to be a very difficult thing to define. We'll know it when we see it. Tim Rumpf. Let's try this one more time. If you could have a smallish cloud of gas and dust, could it form a central gas giant or brown dwarf with satellites? I'm reluctant to call them planets orbiting it. Has anything like this been observed? This is a question that just refused to get answered. So this idea, right, you know, can you just have a planet just form in place and not be a star? And the answer is probably yes, right? It all depends on how much gas and dust that you have to work with. If you have a ton of gas and dust, you're going to get a supergiant star. If you have less gas and dust, then you're going to get a star like our sun. And if you have even less, you're going to get a red dwarf, the minimum amount for it to even ignite with fusion. And then smaller than that, you're going to get a brown dwarf, which is going to use a different kind of fusion. It doesn't use the regular hydrogen into helium fusion, but it can use deuterium instead. And then if you went smaller than that, why not, right? You could have something like Jupiter just form in place. Enough gas and dust gets pulled in together under its mutual gravity and it forms an object that has about the mass of Jupiter. Below that, I mean, part of the problem is that in a place like our solar system, we've got these various processes that are differentiating the different kinds of elements. So for example, here in the inner solar system, you've got the sun that's made of hydrogen and helium, and then you've got this accretion disk around it where all of this material was gathering in the initial disk. And then the radiation pressure from the sun, as the sun ignited, blew out the lighter elements, leaving the heavier elements. And that's why we have a lot of rocky material here on Earth. If we didn't have a star, then we probably wouldn't have had all that volatiles blasted away, and we would have something more like gas giants. So could you go smaller and smaller and have smaller and smaller gas giants? Sure. You know, whatever is the smallest amount of hydrogen and helium that can collect together into a ball, you will probably find out there. But the problem is that we can't see them. Because they're not big enough to release fusion energy, we're not going to be able to see them. We can only detect them through other methods, like the effect of their gravity, or maybe through gravitational microlensing. It's one of these passes in front of a star, changes the light of the star for a moment before it passes along. So there's no reason to expect that we wouldn't find stuff out there. The problem is that they'll be very, very difficult to see them if they're not either releasing light as a star or reflecting the light from a nearby star. They're almost impossible to find. Hiroshi loves you. Is currently any spacecraft in planning which could serve the Hubble telescope? No, the last spaceship that was capable of servicing the Hubble Space Telescope was the Space Shuttle. And of course, the Space Shuttle stopped flying in 2011. And A little before that, they did their final servicing mission. They gave it tons of gyroscopes, tons of additional propellant. They upgraded all of the instruments on board, and they set up Hubble so that it could last as long as possible. They also put in a way for it to deorbit itself at the end of its life. So when Hubble finally does break down, probably in the next 10 years or so, it's going to deorbit back through the atmosphere and burn up and be gone. Now, there's nothing that could repair it today, but who's to say what's going to be coming down the pike in just the next decade, right? Could you send a Crew Dragon with an additional service bay attached to it that astronauts could go and do that work? Maybe. Could a Starship go and just gobble it up, bring it back down to Earth, get it fixed up, go back to space with it? Maybe. Or Starship could go, come up beside Hubble, and astronauts could do the work. So we're right at this edge between this entirely new revolution in spaceflight, and we don't know what the future is going to hold. So we're just going to have to wait and see what happens. But right now, there are no plans to service Hubble. When it dies, dies. Jay Pearson, trying to understand orbital dynamics. When you say boost the station up, is the actual maneuver to accelerate the station forward, or do they thrust perpendicular to the center of the Earth? Yeah, when I say boost the station up, all I mean is increase the space station's altitude from the surface of the Earth. So, and the way you do that is exactly right. You don't boost perpendicular to the Earth, you boost in the direction that the space station is flying. You essentially increase the space station's velocity. And the weird thing is that that then raises its orbit and decreases the speed that it's orbiting the Earth at. Play Kerbal Space Program, you'll understand how this works more intuitively. But yeah, so they shoot in the direction that the space station is going, and that raises its orbit. And of course, if you wanted to do the opposite, if you wanted to lower the orbit of a spacecraft, you just fire your propellant in the opposite direction that your vehicle is traveling, in the opposite direction of your orbit. That lowers your orbit, ironically speeds up your speed going around the planet, and you're closer to the surface of whatever it is that you're orbiting. And if you want to do something more complicated than that, generally, again, play some Kerbal Space Program. There are ideal times when you actually fire that thruster to increase your altitude. So, but yeah, in the direction that you're flying or against the direction that you're flying. JT Likens. Hey Fraser, thank you for all your hard work. If it was possible to fly the speed of light to, say, a star 10 light years away and send a message back to Earth now, how much time would go by on Earth versus the spaceship? Now, of course, it's impossible to fly at the speed of light, but let's just assume that you could, for the math. If you could fly at the speed of light from Earth to a place 10 light years away, you would experience no time from your perspective. So you would turn on the spaceship, you would arrive at your destination from your perspective. It would just be like click, click, and there you are. Speed of light, you've done that. Now, from us here on Earth who watched you go, we would watch your spaceship fly through space at the speed of light for 10 years to get to its destination. Then you would send your signal, and it would take an additional 10 years. So when you leave to when you arrive 10 light years away, that takes 10 years from our perspective on Earth. You send that signal, it takes an additional 10 years, so the total time is 20 years. From your perspective, you turn on the warp drive, the light drive, you arrive at your destination instantaneously, and then you send your signal back at Earth. You then have to wait 10 years for the signal to get to Earth, and then 10 more years for the signal to get back to you. But we can't travel at the speed of light. Manimus 11. Unless we figure out how the Alcubierre warp drive works, and even if it is possible, humans will never be able to travel the universe. But if we can find a way to change our DNA or our bodies so that we can live for hundreds of years, maybe we can have fun in our galaxy. Lol. It shows how difficult it's going to be for us to comprehend what the future holds when you think about these problems. What does the fact that, say, modern cell phones, smartphones have been around for 10 years, 12 years, and they've dramatically changed everything on Earth, that medical technology is accelerating, artificial intelligence is accelerating. We have all of this technology that affects us here on Earth. It's going so quickly. And yet then we think about these things like, what would it be like to travel 1,000 years, 10,000 years on some generation ship to get to another place? And so we think about ways that we could slow or make that journey possible through modifying our DNA to live forever. But if we could make ourselves live forever, that would have all kinds of implications, the least of which would be being able to travel to another star system. But just think about what that would do to planet Earth if nobody died. I'm sure science fiction authors have thought about this all the time. So practically speaking, it doesn't feel like there's going to be any way that just human beings themselves are going to fly to some other star system in a reasonable amount of time. We did this video called the weight calculation, and you calculate when it will happen in a fairly short period of time, and it's still about 700-800 years away. If you just increase the amount of energy that we're expending, and you look at the amount of energy that it takes to travel to another star, in about 800 years, those will overlap, and you can get to another star system in a reasonable amount of time. And then, of course, when you think about how long humanity's been around for, 700 years is actually not a lot of time in the history of humanity compared to the million years or so that human beings have existed. So I have no answers. I have no answers about when any of this stuff is going to come about, what technology this stuff is going to look like, and what we're going to look like when it actually does come about. It's all moving so quickly. And I feel like whenever I try to think about this, it's like you're trying to unravel a ball of string or something, because it's just so complicated to wrap your mind around. So again, I have no answers. I find the process fascinating, and that's kind of why I like to stick to the really close future stuff, because I feel like the distinction between what we can know and what is reasonable to assume just falls apart beyond a certain point into the future. Brian. This is total BS. It doesn't work that way in science. If you want to say something is a black hole, you prove it. Is this guy really a doctor? No, that's not how science works at all. Science works in that you see a problem, an issue, there is a mystery, like what happens to stars of a certain mass when they die? What is the enormous amount of gravity, some kind of massive, highly dense object that we seem to be finding at the hearts of supermassive black holes? What are quasars? These are questions, right? You can take a small telescope, you can look up in the sky, and you can see a quasar if you want. Some of the brightest ones are visible, and yet these things are billions of light years away. You shouldn't be able to see one with a telescope, and yet you can. With a backyard telescope, you could see a quasar. So then what is it, right? How can this amount of energy be being focused like a point-like source across billions of light years away? Or all of these other different mysteries that I mentioned. And so then astronomers come up with a hypothesis. Okay, here's one hypothesis. It's a black hole. And then they say, and if it is a black hole, then we would be able to take a picture of its event horizon. We would detect the collisions of them through gravitational waves. We would see their gravitational interactions with other objects. We would see them giving off high levels of X-ray radiation from seemingly nowhere. We would be able to detect them as their mass moves in front of some other object, and a whole bunch of other tests. And so you make these hypotheses, and then you search for the evidence to see if that hypothesis is correct. Imagine if the Event Horizon Telescope took its picture and it got that beautiful ring of all of the material of the event horizon, and then right in the middle was a happy face. Suddenly, black holes disproved, just like that, right? You make a hypothesis, you're expecting to see that empty part in the middle, you take the picture and you don't see what you're expecting. So you throw out your hypothesis. That's how science works. And so if you or anybody out there on the internet says that they have some alternative hypothesis for what these things are, what happens to a supermassive star when it dies, what is the dense, massive object at the heart of many galaxies out there, what is causing stars to move in little circles around something that's invisible, all they have to do is explain, provide a hypothesis and then test that hypothesis, right? Is it some hologram? Great, what would a hologram look like? How can you prove that it's a hologram? Maybe a hologram would shimmer in a certain way. Maybe a hologram would not just be distorted through gravity in the ways that black holes do. You can make all of these predictions for whatever hypothesis that you have, and then you're attempting to disprove your hypothesis. So what we went through in that video was exactly how science works. Make a hypothesis, attempt to disprove it. If the hypothesis holds, then it is still your best guess, still your best theory on what it is that you're looking at. And of course, future evidence can always come along that disproves your hypothesis and you have to throw it out. And that's also how science works. And scientists are totally fine with that. They can't wait to have their hypothesis disproved because it gives them one more piece of information that gets them closer to the truth. Disasterina. Can we tell if any stars have gotten closer than Alpha Centauri to Earth in the last 100,000 years or so? Yeah, we can track the movements of the various stars in the sky. And thanks to the Gaia telescope and other really precise astrometry telescopes, we can track these movements incredibly precisely. And so I was then able to find some really good information on the past of these objects, but I was able to see the future, and it's really interesting. So Proxima Centauri and Alpha Centauri aren't as close as they're going to be. In the next few tens of thousands of years, they're going to get within about 3 light years of Earth. And other stars will be doing that again. So probably within the next 100,000 years or so, we're going to have about 10 stars get within about 4 light years of the Earth before they move away from us again. And so if that's just in 100,000 years, you would expect that over millions of years, stars have gotten a lot closer to us, probably within a light year or two. Reme Wallet-Perez. Hey Fraser, I'm having difficulties understanding one question. Why is it that you can't escape once you fall into the event horizon? Considering you or any matter fall into the event horizon, but then got pulled by another greater power like another black hole that just happens to pass by, what happens then? Well, the definition of the event horizon is that is the point as you near the black hole where the escape velocity that you have to be going exceeds the speed of light. In other words, the only way for you to escape that region of the black hole is to be traveling faster than the speed of light. And by the laws of physics, you can't travel faster than the speed of light. Therefore, you can never escape the black hole. And even if another black hole came super close and was pulling on you with its gravity, it wouldn't be able to pull you out of the event horizon of that other black hole. And more likely, it would be pulling that other black hole into itself and the two would merge together. But still, there is no force, no way, nothing can escape unless you can travel faster than the speed of light that you can get outside of the event horizon. And even if you could travel faster than the speed of light, as I mentioned before, actual space-time gets tangled up so badly that there are no pathways that lead you out from the center of the black hole. You're going in, there's no way out. Aniello Di Meglio. Aren't black holes an infinitesimal point in space? I'm getting confused between the terms black hole, singularity, and event horizon. Yeah, so when you think about a black hole, the part that we can see in that image of M87's supermassive black hole, that is the region around the event horizon. I think it's the photosphere and around that. That part that I mentioned, that point where nothing can escape the black hole, that is the event horizon. And it is just an arbitrary line in space. If you're a little outside of that region, if you're traveling the speed of light, you can escape. If you're inside that region, if you're traveling faster than the speed, or as fast as the speed of light, you still go inside. What's in the middle? We don't know, right? We know what's gone into it. We know that stars and planets and gas and dust and light and antimatter have all gone into the black hole. They've all crossed the event horizon. But what actually happens to them inside that event horizon is unknown, and it might be never known. One possibility is that it's some more exotic form of matter, take say a neutron star, which we can see. A neutron star is right at the limits of becoming a black hole. We can see them. Their escape velocity isn't faster than the speed of light. Therefore, light can escape a neutron star. They're very bright, they're very hot, we see them. You add a little more mass to a neutron star, that event horizon, right, starts to show up because it has crossed the amount of mass required in a dense enough region that not even light can escape it anymore. And so maybe inside that event horizon, just below the surface, there's the black hole, but the black hole is actually some sphere made of some kind of exotic matter. Or maybe the forces that are compressing it down just continue to smash it down and make it smaller and smaller until it's infinitely dense. Or maybe it is attempting to become infinitely dense. It's just getting smaller and smaller and smaller, faster and faster and faster. The bottom line is that we don't know, and we might never know. The problem is that there's no way to be able to see inside the event horizon. Drew Pennington. So is the shorter orbit time the reason why so many discovered exoplanets are hot Jupiters? Have we just not had sensitive enough equipment looking long enough to see systems like our own? Essentially, yes. The exoplanets that have been discovered so far are the low-hanging fruit. The largest planets, planets with several times the mass of Jupiter, orbiting really close to the star so quickly that the radial velocity pulls the star back and forth, that we can measure it, or a planet that passes directly in front of its star very rapidly every couple of weeks so that we can confirm the discovery. The probably more common but less easy to find ones are what are going to be the vast majority of the exoplanets that we're going to find over time. Take a planet that's half the mass of Jupiter, that's orbiting, that takes twice as long as Jupiter. Well, in that situation, the chances that it's going to be perfectly lined up with the star are very low. And even if you do see it pass in front of the star, you then have to wait 20 years, right? 10 years for it to pass in front again. And then you have to wait another 10 years. We haven't really been studying exoplanets for that long. So over time, as we develop better technologies, as we just do this job longer and longer and longer, more and more planets. And a lot of the more interesting ones, I mean, I guess a hot Jupiter is pretty interesting, but some of the ones that are farther out, some of the ones that are smaller, more Earth-like. And so consider finding another Earth. You would need to see a planet that is far enough away from a sun-like star, and it would be Earth-sized, and it would have to pass directly in front of the star. But then you would also have to confirm that discovery. You would need to use the other technique. You need to use the radial velocity technique to measure the wobbling of the star as the planet is passing in front of it. And you'd have to do that over the course of several years. You would see one pass in front, you'd wait another year, you'd see another pass in front, you'd wait another year. And so now you think, okay, we think we've got a planet. You wait another year, you get another pass in front. Now you're pretty sure, wait another year, it's 4 years, 5 years, right? After a while, you can be like, okay, we're very sure that we've seen an Earth-sized world orbiting around a sun-like star in the habitable zone, but it's going to take a long time. So we are just so far just at the very beginning of exoplanet discovery, and over time, the discoveries are just going to build up and build up. But for now, it's the extremes that we're discovering, and that's the way it always is, right? We recognize the most extreme objects first, and then we find the less extreme objects over time as we get better and better at our observations and our technology. Lori, why is ISS on the height where it is? Why not farther away? We talked about how the International Space Station needs to be boosted on a regular occasion to stop it from re-entering the Earth's atmosphere. And so you might say, well, like, why have the ISS so low? Why not have it higher so it doesn't have to be going through so much atmosphere and it doesn't have to be reboosted? You're right, but it's important to understand that it's like it's on a mountain, right? A mountain that gets you farther and farther away from the surface of the Earth. And the higher you go, the farther out of the gravity well that you go, the more energy is required to build the space station and the more energy that's required to resupply the space station. And so when NASA was developing the space station in the first place, they did all this math and they said, okay, what is the optimal height where you will still have to boost it on a regular basis, but you can put as much cargo into space to be able to actually build modules onto the space station or be able to resupply it with as much cargo, heavy equipment as you could without it actually burning up. And where the International Space Station flies right now is that sweet spot. If it flew higher, it would have been a lot more complicated, a lot more expensive, and required a ton more fuel to build it in the configuration that it is, as opposed to just every now and then launching more fuel and boosting its orbit back up again. So it was a balancing act. This was the orbit that made the most sense for all of the mission parameters that NASA had for the space station. All right. This ends the question show. Again, I have a lot of fun with these. Thank you everybody for watching. As always, if you have a question, pops into your brain, just write it down, I'll gather them up, and I'll answer them here. I'll see you next week.